All right, oh, it is amplifying. All right. Hey everyone, welcome back from midterm weekend. I hope you were able to not think about 373 for maybe at least 24 hours. But since we are starting a fresh unit today, the poll everywhere question is just like a check-in. So like, I'd love to hear from you. I will read all of these at some point, and I will read them anonymously if that helps you feel better. But go ahead and upvote. What are our vibes? How are we feeling at the moment? Shout out to this imagery, the rubber ducky. Doom. N factorial. That, if you want to be a nerd about it, our brains are probably running an n factorial at all times, aren't they? Something about infinite connections. Also, something about constant graph searching. That'll maybe make sense in a couple weeks. Yes. Oh, you delightful nerds. I like it. Analyzing best and worst case of my grade. I will also tell you we are hard at work grading. We're also working on all of your wonderful regrade requests and all that type of thing. And then I usually do like a twice quarterly migration into Canvas. I'll do the first one hopefully this week, where I'll try to take all of your scores that are in Gradescope and move them into Canvas so they have like the weights and any late stuff applied, so you can get a kind of sense as to where you're stacking up. I know on the course syllabus, I have what I call like my minimum guarantee GPAs. I just want you to know they literally are minimum GPAs. I have to give myself a lot of sort of wiggle room there. So sometimes people look at those percentages and it's like, whoa, I can't remember what they are off the top of my head, but it's like, whoa, those seem really harsh. That's just my minimum. The actual GPAs usually end up being much higher than those numbers I put there. But for obvious reasons, I don't want to overpromise, and then you get a score lower than I promised you. That feels the wrong way to err. So I promise I'll be putting a lot more sort of grade stuff in there. I also just want you to know, like right now, if you are feeling some type of way about how you're progressing towards your ideal GPA in this class, I would love to talk to you about it. I know it can be weird sometimes to talk to a professor about your grade, especially if maybe the conversation's about how it's not where you want it to be, but it is literally my job to help you be successful. And I promise, I don't care what your grade is. I don't think grades are a reflection of almost anything other than your ability to come and like sit in this room on a regular basis. So I would love to chat with you if you have any concerns at this moment in time. Usually I don't get anyone taking me up on that until after the midterm, because stuff just gets real after the midterm. So if you want, please feel free, use my bit.ly, sign up for time. Always happy to chat grades or to help you work towards a shared goal. Let's see, I am dead. Aren't we all? Inside, certainly. You seem a bit nervous. Yeah. Vibes. Okay, great. Oh, dear God. Was it that mean? Oh, no. Okay. Love this. Okay, I'm not going to lie. I want you to know me and the TAs talk about this on the regular. For context, like I said, I hate traditional assessments. And for like the last 4 years, I have been changing the format of the assessment constantly to try to get to something that feels a little fairer. This is actually only the second time we've ever done this particular format, where I give you like these design questions and then you get the resubmission thing. So that's part of why we don't have as many prep materials, because it's like kind of brand new. But we will be talking about it. A lot of the TAs were like, we should give students more resources. So thank you. 4 more weeks. Yes. Got it. Yes. Don't we all? All right. Okay, shout out to you. Shout out to you, person. We want to celebrate this delightful spectrum of feelings. Incredible, decent. Yeah, I know that, like I said, this is a new format of midterm, and we're constantly working to make it as predictable for all of you as possible and all that good stuff. But remember, it's got to be a little bit difficult to make it interesting enough to do the resubmission. And I kind of care more about like, after y'all have consulted with your textbooks and each other and thought about it and reflected. And so I know that after the initial in-person midterm, it can feel not well or like you're going to die. But hopefully that resubmission, I will tell you, most of you end up getting a very, very good score on the resubmission. And we will be releasing what we consider to be the common mistakes. We can't talk about the actual answers yet because you got to do the resubmission. And then we'll talk about the answers a ton. But we will kind of give you the like wink, wink, a lot of people misinterpreted this question kind of stuff, because we really do want you, like honestly, our dream is that you all get 100 on the resubmission, and that grading just goes like whew, so fast. So I promise we're rooting for you. These are incredible. Oh, hang on, I'm going to cough. Please feel free, like I said, I'll look at all of these in some amount of order. But does anybody have any sort of, yeah, please.
Wait, so when the tests are returned to us, do we know which questions we got wrong?
Great question. Let's officially segue into talking about all of that. So, okay, so what's going to happen now is we collected all of your exams. For reference, we scanned them all into Gradescope. So they are now sitting in a Gradescope assignment. We are going to return that to you where you are going to see per box even what your score was in terms of numbers. So you are going to know exactly your score on the exam. We may not show you the rubric items that you missed, but we will show you what your score was for that item. And so then it's up to you to reflect, talk to the TAs, be in community with one another, and then revise any of the questions you would like to revise. For example, if you got 100% on something or you did really well on something and you just don't want to bother to resubmit it, you don't have to resubmit it. So it's just up to you how much of the exam you want to resubmit. We will grade that exam as if it's its own independent standalone. So as you can imagine, that's why we're like, we hope you all get 100% because that grades so fast. And then we just average those two scores together, which mathematically is the equivalent of saying you can earn up to half of your missed points back. So if you got a 50 on the in-person one and you got 100 on the resubmission, you end up with a 75. Does anyone have any questions about how the resubmission is going to go? Right now, we're tracking to be done with grading probably on Friday this week. And so I'll show everyone sort of like what our nice little numerical layout is and all that stuff then. You'll get your scores. You'll have a week to resubmit, and the resubmission will be via Gradescope. So it'll be a Gradescope digital. You can type instead of write on these crappy tabletops kind of thing. Yes, question? What is the estimate of the average score of the resubmissions? I can only tell you one other quarter's worth of data, but like last year, I want to say the resubmission, the average score was like in the 90s. So most of you end up doing really well. This is the moment where students are like, Casey, somebody in the class was talking to somebody else in the class at Odegaard about the exam, and I'm supposed to be like, oh no, it's an individual assignment, but here's what I am going to say. Okay, like, I get it. The reason we forced you to do this in-person thing is I feel I've already captured at least what you can stuff in your brain. The TAs cannot tell you the answer to something or say pre-grade something for you, but you can ask the TAs conceptually like, oh, maybe I misunderstood this thing about hashing, or oh, maybe I misunderstood what in practice runtime means in the context of this structure, or something like that. You are welcome to talk to the TAs. You're welcome to talk to each other. You're welcome to come talk to me. Do whatever you got to do to get the assignment done. And so I do sort of know that a lot of your results in the resubmission will hopefully be in response to the community discussion that I know happens. That's my sort of way of like doing this hybrid between people that it's all in your brain, it's timed, it's here, I know it's just you, and the reality of how we all get work done. So that's why I do this sort of hybrid thing. Also too, because I think sitting in this room with everyone like breathing, hunched over their desks is not the most conducive to everyone's brain working properly. So hopefully when we give you your grades, we'll open that online GradeScope assignment and you'll have a full week to do that resubmission. I don't think it's going to take you a week. It took you 50 minutes to do the exam. I hope the resubmission is something that's like, I talked to some other people, I had some shower thoughts, and then I wrote it down, and maybe that's an hour or two of your actual working time. But you have a week to find the most peaceful, clear moment in your day and in your environment to do that work, as opposed to when I asked you to do it in this room. Any other questions about how the resubmissions work? We're going to do the whole thing again in week 9. So it's going to feel a little weird. It's week 6 right now. We're going to give you these grades. You're probably going to get your grades back finally from the resubmission sometime in week 7. And then in week 8, we're going to be prepping for the next one. I know that's just how these 10-week quarters go. But also, if you have any experiences, feedback, requests of us, we would love to hear it, especially because we can actually maybe do something to make your life easier, better, kinder, inclusive between now and week 9. So if you have any thoughts, feelings, please feel free to share them with us. Other sort of just updates as far as things go. Remember that the exercise 3, the trees exercise, that was the one we pushed that deadline out. That's now due tomorrow. So just a reminder to you. We released P3 on Thursday last week. And I'm going to be honest with you, I usually give students 1 week to do that assignment, but it just felt like there was a lot of deadlines flying around and it was ready to go. So I was like, let's release it. It's not due this week. It's due next week on Thursday, February 15th. But you should know that one is historically a 1 week's amount of effort. And this is me trying to give you that time because I'm asking you to do the resubmission on top of all of this. And I know that's unkind to have so many things flying around all at once. But plan accordingly. If I were you, I would get started on P3 now because then you can do your resubmission next week. Also, we just talked about heaps, so maybe they're fresher in your brain now. But listen, you're the captain of your own ship. Okay, I think those were all my administrative things I had to say. Does anyone have any other administrative questions? Okay, cool. All right, let's squeeze this rubber ducky. Let's talk about something new. Let's talk about graphs. Honestly, this course is kind of divided into survey of data structures and then graphs. Welcome to part 2. So, once upon a time, you met the array. You had maybe learned about variables, which were individual pieces of data, right? And then we introduced you to this thing called an array, where you could take multiple pieces of data and put it together, which is kind of how it works inside the computer. But this is actually a really loose structure in terms of that each of those pieces of data don't have any sort of official relationship other than proximity. Maybe when you're designing something, you've decided, well, it's sequentially sorted or everything that's in this array is somehow related because they all happen to be stored together. But there's no official part of the data structure array that dictates anything about the relationships of those data other than they happen to be somehow associated and they're in one big grab bag together. I kind of think of an array as a bookcase. So maybe at least they're all books, but we don't really know how they're associated otherwise. Then we got real into trees, right? And there's a lot of different organizations of trees, hopefully you've learned at this point. We have, binary search trees, like AVLs and things like that, where we've got data that is related. We've got parent-child, we've got left-right, so we've got some order. We also have this idea that there is a hierarchy of relationship, maybe in the min-heap situation, the thing with the minimum priority sitting at the top and the priority decreases in levels. So trees, where you have these individual entities, the nodes, and then you have the connections between them, the existence of how those connections form kind of starts to give us some amount of relationship data. A lot of people at this point start to make that family tree analogy, that there's some type of hierarchical relationship inherently communicated in how that structure exists. Now, people use trees for lots of reasons. Maybe the things don't have any hierarchical relationship, like BSDs, it's just ordering. But we are now moving into a new space. We're calling these graphs, where every piece of data is no longer just its own individual piece of data, but we are constantly obsessed with that piece of data's relationship to everything around it. And now, instead of only dealing with the entries as pieces of data, the relationships themselves must also be accounted for in how we store them, how we navigate them, and also runtime analysis. Yay! So, graphs. Everything is graphs, as it turns out. Literally everything we've studied so far, technically by definition, is a graph. Binary search trees are graphs, because all trees are graphs. Linked lists, technically graphs. They're pieces of data with relationships to other pieces of data. Heaps, all of that stuff. We have a data entry and then a connection to go from one data entry to another. Now, we've assumed that relationship to just be ordering, but what if you could add details about what that relationship, what that connection means? Also, pretty much most complicated software products out in the world are built on graphs. We live in the data revolution. The world is full of complexities, and now we have something to represent the complexities of the human world. So, Google Maps database, it is a graph database. All of those little hyperlinks between different web pages are relationships to get from one web page to another. Facebook, if you start typing in any of the boxes on Facebook, because I'm sure all of you do that, you're definitely of the Facebook generation. Technically, this applies to Instagram search as well. That's called graph search. It's actually navigating between profiles, where profiles are an entry and likes or shared groups or common hashtags or behaviors are all different relationships between you and other entities. GitLab repository history, a graph. Technically, you start with an initial version, and then maybe you fork it, and your neighbor forks it, and your TA forks it, and you all do things, and you bring them back together, and you have those arrows. You can even see them in GitLab for how the different versions of your repos are related. Secretly a graph. Prerequisites, family trees, all those things are graphs in terms of they are an entry of data and how it relates to the data around it. Yes, please.
Is it fair to say that graphs are a collection, a umbrella term for types of data rather than a specific data structure?
Ooh, okay, yes, good question. So if you asked every software engineer, they would probably give you a slightly different answer to that question. So a graph is not really a data structure or an ADT. It's kind of this umbrella term because so many things can fall into that category. But you can probably think it's closest to a data structure in terms of it's an idea of how to literally store multiple pieces of data in a structured way together. But the key is that what makes it a graph is just when you have data and the relationships between that data are both pieces of information you're going to maintain and need to consider. So it's like data structure asterisks. That kind of answers your question. Here are a bunch more applications. You will encounter this a ton, especially in interviews, because software engineers cannot stop thinking about graphs as physical maps. So an airline map, the vertices, that's a word you're going to hear me use a lot. That is the graph version of node. Vertice is what we are going to call a data entry, and edge is what we're going to call the relationship. So in an airline map, maybe the vertices are all of the airports, and the edges are all of those like flight paths. I'm pretty sure that's what this is a picture of. Also, Google Maps, just a big old graph where every single address is a vertex, and the roads between those addresses are the edges, but Google Maps stores time it takes to drive at the speed limit, time it takes to drive at every hour of the day according to traffic. Maybe it takes how long it takes to walk versus it takes to ride a bike. Maybe it includes topology information. All of that type of information might be stored along the edge. so that you can calculate all the different ways to travel from one address to another. That's all technically a graph. Relationships, a very common one. I am pretty sure this is a picture I pulled from a graph research blog representing influencers on what was then called Twitter. So in this particular context, socials, anytime you have a profile, that's probably your vertex, and then following or followed or commented or liked or shared, those are all different types of edges or relationships that interconnect those individual pieces of data. Influence is another popular form of how to map graphs. This is an area I know absolutely nothing about, but I stole this from some biology researcher. And my understanding is that proteins often have similar structures and they can influence one another in different ways. And so actually a lot of how the data is stored in terms of biology, and I'm sorry if I'm saying things that don't make any sense, you probably have better biology than me, you can have the different molecules or the proteins and the different types of actions they may take on one another represented as the edges in between. And then, of course, related topics. I'm pretty sure this top one is web page rankings. So keep in mind the way that Google decides what to show you when you type something into the search bar is because they have something called a web crawler that navigates the internet via the hyperlinks that take you from one page to another. And if a lot of pages are linking to one page, Google's like, wow, that page must be really relevant. People keep talking about it. And so it becomes a bigger and bigger hub. It grows on the search engine results. There's a bunch of other like secret sauce stuff behind the scenes as well. You can get into that. Wikipedia also is a giant big graph where the vertices or those nodes are each individual Wikipedia page, and all of those hyperlinks, those are edges. You ever get in those Wikipedia rat holes where I was just trying to look up that actor whose name I couldn't remember, and now suddenly I'm on the nuclear physics Wikipedia because I clicked on too many hyperlinks? That's you just navigating this graph. So I give you all of this context because really what a graph is a way to start to codify the complexity of the human world. And then what I'm going to show you is once you take the complexity around us and translate it into this form, a bunch of researchers have gone out there and found really useful algorithms that you can just run over your graph and then get really useful information back. Things like shortest path, things like minimum spanning tree, things like BFS and DFS, things like toposort. So once you can figure out how to translate the human world into this particular structure, then I have a lot of tools that you can just plug and chug to get some really interesting questions answered. Oh, there, allthingsgraph.com. I think I pulled a lot of these from there. Great. Okay, let's get a little more formal. So here's how you might see us represent graphs. They look kind of like a tree where there is not really any particular start or end. So a graph is defined by a pair of sets, V and E, where V is the set of vertices. That's the node. So here we've got, A, B, C, D, E, F, G, H. Those are the set of vertices. And then E is a set of edges. And that's all the connections that happen to exist. So you can see A, really well connected. It's got a connection to H and to D and to C and to B, versus F or maybe E. You've only got one connection to D. But that's fine. We have total flexibility in the graph definition for how things are going to be connected together. But if you've noticed, I have not used N at any point. And that's because now when we think about the runtime and the complexity, we have two variables to keep in mind, V and E. V for vertices, or those sort of like data entries, and E for edges, or the lines between those vertices. Any questions so far in the formal definition here? Great, let's talk more vocabulary. Okay, so within a graph, you can have directed or undirected edges. So if you have an undirected graph, a singular connection, I like to think of that as a two-lane road. Jim loves Karen, and Karen loves Jim. It's bi-directional. Jim loves Pam, and Pam loves Jim. Tricky. But a directed graph means you can only leave from one vertex and arrive on the other vertex. So Gunther loves Rachel, but Rachel loves Ross, and Ross loves Rachel, but there is no love from Rachel back to Gunther. These are still relevant pop cultures, right? Yeah, okay, thank you. So directed, it's got to have little arrows, and you can only travel that one way. Undirected, there's no arrows, and it means every edge is bidirectional. You may hear us refer to the word degree. Degree means the number of edges connecting to a vertex. So you can imagine a social media influencer that has a lot of followers. It's got a very high degree. Now, if it is a directed graph, they may have a difference between in degree and out degree. So maybe you have a website that has a lot of really relevant information and a lot of people link to that website. It has Hello? Hello? Oh, there. That seems to have resolved it. Yes? Great. Gunther is a very kind-hearted and patient, loving individual who so thoughtfully served Rachel coffee every morning only to be ignored by her for the entirety of that series. Yeah, question here in the middle. You're right. Jim should have a degree of 2. I agree with you. Cool. Sorry for the typos. Yes, please.
What are the benefits to using
What are the benefits to using one versus the other? So it sort of depends on the situation you're trying to represent. You know, for example, if we're doing a Google Maps situation, there's a lot of one-way streets, right? So we have to use directed because not every street is inherently going to be bi-directional. But maybe we are representing walking paths. Well, walking paths aren't really directed, right? You can kind of walk both directions usually, so maybe that's undirected to represent that you can walk either direction down a path. So it kind of depends, and as we get deeper into the algorithms, you're going to see that some algorithms require that your graph is directed or not directed. Let's learn some more. Okay, so also, we are going to refer to things in terms of connectivity, and this is the part where brains tend to break. This collection here, this set of 4 vertices and only 2 edges is a valid graph. But J is not connected. That's okay, because the way that we are going to structure graphs is 2 separate sets. So you might have a vertex in your set of vertices that has a degree of 0. it is maybe unreachable, that is valid. Same thing here. We've got a directed graph. In this context, you can get from A to B to C. D is totally unconnected, but that still is a valid member of the vertex set. And in fact, we are going to have to figure out which algorithms we can use to navigate in these contexts. You can see some definitions here. I'll let you read them. But you may also hear me say the words path. Path means if I was to start at one vertex and follow the edges to another vertex, that's a path. So there is a path from O to N. I could either go O, P, M, N, or I could go O, P, I, M, N, whatever. Those are examples of paths. Here, there is a path from M to N, but there is no path from N back to M. So I could only, if I think of myself as a little, I don't know, island hopper, or maybe I'm just like a walking down Google Maps, maybe I'm like the Google bot or whatever, I can get from M to N, but I can't get back the other direction. No path exists. A cycle is when I can leave one vertex, walk along edges, and return to that vertex. So in this undirected connected graph, there's a cycle. I can go from I to P to M to back to I. But in this connected graph, there does not appear to be as many cycles. For example, I can go from I to P to M, but I cannot get back to I. So there is no cycle there. And again, I'm giving you these words because some of our algorithms will say it doesn't work if there's a cycle, or if a cycle happens, you have to do something different, things like that. So I'm just giving you all the tools to represent the complexity of whatever relationship you're trying to represent. There you go, acyclic versus cyclic. You can see here we've got a cyclic graph where I can leave C and come back to C. This is a situation, again, where there is no cycle. That's where the cyclic comes from, acyclic. There is no cycle, so if I leave C, there is no way to return to it. Just more examples of how to use this language. Now here is how we are going to start to represent some of that data associated with the edges. So like I said, technically, the way you represent a graph is just a set of vertices and a set of edges, but each of those edges may themselves contain information, just like the vertices may contain information. Now, we're probably a little more comfortable with the vertices. We're used to having nodes where maybe they have a data field, and maybe we even have more complicated nodes like a trie node where it's got a data field and it's got a is entry or not entry Boolean. That might happen here. We might have vertices with multiple pieces of data. Well, we might also have edges with multiple pieces of data. You'll often see us write things like this here where we've got both vertex and edge weights. Very common. Most of the things in this class, just for clarity's sake, I'm going to give you one piece of data in a vertex and one piece of data on an edge, but never forget that we could store as much as we want in any given node. We could store as much as we want associated with any given edge. Like I said, maybe Google Maps has the time to walk, the time to ride a bike, the time in heavy traffic, the topology. All of those things are pieces of information associated with a particular edge. Maybe they store them in different ways. But this is how we're probably going to talk about our little, theoretical friction-free graphs where I just give you one piece of each because that's kinder. Okay. This is just more details that you can read at your own leisure that says now the value n in context of the graph no longer applies because there are two variables that dictate runtime, E and V. So remember, when Casey tells you on the final exam, if I ask you for the runtime of any graphs and you write O of n squared, no. There's no n. There's no n in graphs. So if I ask you for the runtime of a graph, it should be O of some type of V, maybe plus some type of E. The n still applies to the other ones, but in graphland, two variables, V and E. Yes? Yes, similar to that, right? Like when we were talking about the try, for example, it was like, oh, well, the number of entries seems to dictate how long it takes us to find something, but also how long each of the strings are does too. So we were starting to hint at some multivariable. Similar idea here. We can't think about the runtime of a graph without thinking both about the number of vertices and the number of edges. Let's talk about how you actually will encode these things in Java. As it turns out, there's a lot of different ways to represent graphs. I'm going to teach you about what I think of as the most common or the most popular, but there's even more ways than this. You could, for example, make a new object called graph, and it could have objects inside of it called vertex and edge, and you could navigate them with references. You could also just have a collection of collections where you have a set of the vertices and a set of the edges, and maybe you have a hash map from the vertex to its value and a hash map from the edge to its weight, something like that. But here's one of the first ways you can start to think about it. We call it an adjacency matrix, where it is a two-dimensional array where it has the same number of rows and the same number of columns, so it's always a square, and that represents the vertices. So you can see we have here all of the vertices listed above, and here all of the vertices listed above. Now in this particular one, this is an undirected graph, so you can see here there exists an edge between the vertex 0 and the vertex 1. So in row 0, column 1, I have put a true entry, which is often represented with the value 1 in computers. You could do this as a Boolean as well, but you'll find most people do it as an int in this way. But because it is a undirected graph, that means that there is also a way to get from 1 to 0. So if I go to row 1 and column 0, look, there is another entry for true. So these two red ones right here represent this line between the vertex 0 and 1. So when we think about the time complexity, adding an edge, constant time. Because I can just pop into this two-dimensional array and change any of these values from 0 to 1. So it's really quick to add new edges. If I wanted to draw a new edge between 1 and 4, then I would just go to row 1, column 4, turn that 0 into a 1, row 4, column 1, turn that into a 1. If I wanted to remove an edge, same idea. If I wanted to check if edge exists, same idea. If I wanted to get all of the outgoing neighbors or ingoing neighbors, what I would have to do is I would have to loop across the row and see, and then across maybe the column to see what's connected. And that, because this is an n by n or a v by v graph, I was using n here for your kindness. There you go. So you can think of that as an O of v time. So the space complexity, again, since we have v by v, we are using up that space. I'm not going to lie, this is the less popular of the graph implementations, but you can't leave this class and have somebody say to you, oh, do you prefer adjacency matrix to adjacency list, and not know what adjacency matrix is, and so now you know it, but let's really talk about, okay, ignore those animations. Let's talk about the adjacency list. This is the far more popular representation of graphs, where you have a few different collections. Right now, what we have is probably an array or some type of list that represents each of the vertices. And then in that location of the collection, we have its connected points. So A has outgoing edges to B and to C. So you can see there's kind of like a linked list hanging off of this array entry that includes B and C. B has no outgoing edges, so it doesn't have anything. C has outgoing edges to both B and D, so that's what's in its linked list. So the reason we call this an adjacency list is because really it is a list of whatever is adjacent to that given vertex. So as long as we know which index of the array represents which vertex, and that's probably stored as a separate collection somewhere. Somewhere you have a hash map that's like A, stored at index 0, B, stored at index 1. I kind of made it a little bit alphabetical to make it easier for our brains, but you probably have to have a separate collection somewhere. So adding an edge, jumping in, let's say we just add something new to front. If we add a new thing, then we get that constant time. But you can see this sort of degree from U to V, where we might need to loop over these linked lists to see all of the connections. So the degree of an individual vertex kind of dictates the runtime of checking if an edge exists. Like if I want to see if I can get from B to D, I got to jump into B and then look over its list. That's the best case scenario because B doesn't have any connections. It's a really fast lookup. But if I want to look up A and see if I can get to C, I'd have to jump into A and then loop over its linked list. Not dissimilar to the separate chaining hash table where we dive into a particular index and then we have to look over its chain. So the degree is kind of lambda in this context. So now you can see the space complexity. And remember, I just did this translation for you. So V is N and E is M. The space complexity is exactly however many vertices there are and how many edges there are. It's not just N squared. Now, if that's bigger or smaller depends upon how big N or M is in this context. So you will find that often adjacency matrices are used when you have what is called a dense graph, or a graph where you have more edges than you have vertices. Because it was really optimized for edges, right? So let's say you have like a set number of entries and you're just constantly changing the connections between them. That's when you probably use the adjacency matrix. So it does have a good use case. Most graphs are kind of a vertex forward obsession. So you'll find that they tend to use the adjacency list situation because we don't want to have to recreate the matrix every time we add a new edge or every time we add a new vertex. Because remember that adjacency matrix, we have the rows and columns based on vertices. So if we want to add a new vertex, we'd have to make a whole new array. This gives us more flexibility than that. Can we do better? Yes, we can. Imagine if instead of linked lists, we had hash tables. So this is, maybe going to have a little more empty space because of hash tables, but this is going to give us some really nice constant lookup time. So we've got an array that represents each vertex, and stored in the element of that array is a hash table of every other vertex, so we can quickly look up, does a connection from this vertex to this vertex exist? I'm pretty sure when we ask you, guess what, P4 is a graph-based assignment. Pretty sure this is the situation we're going to ask you to work with. Does anyone have any questions on how we actually represent these graphs in code so far? Okay. This is just me walking through and talking about why you would use an adjacency matrix versus an adjacency list. You can see, really, it's just, are you changing the number of vertices a lot? Don't use the adjacency matrix. If you're keeping the number of vertices stable and changing the edges a lot, adjacency matrix is for you. But if you're changing the list of vertices a bunch, which is most commonly the situation, adjacency list. Great. We are going to assume the hash table one, so we assume that O of 1 lookup kind of runtime, but I will make sure to clarify when we get into all of the runtime analysis. Do I have enough time? Yes, I do for this next section. No questions so far? Okay. Let's talk. I'm going to show you this. I think actually both of these were old midterm problems for years ago, but I'm going to show you some of the things we can do with graphs. So I think we talked about each of these in some context, but again, the internet, the vertices are the web pages, the edges are the hyperlink, a family tree, the vertices. See, look at that's even a duplicate there. The family tree, maybe the vertices are people and the edges are the relationships between them. Graph modeling is the act of taking the human world and translating it into graph terminology. So the first thing you always want to ask yourself is, in my scenario, what is the vertex and what is the edge? And the vertex, I always think of it as like the entity, the data point, and the edge is the relationship. So if you're trying to get from A to B, A and B are your vertices, and however you get between them is your edge. If you're talking about people and how they know one another, the people are the vertices and the relationship is the edge. If you're talking about pieces of software, maybe the version of the code or that commit or that particular computer are the vertices, and then the fiber optic cable that connects them is the edge, or the association in time for where that merge commit, that's the edge. It's the relationship between those entities. So I will, on exams, give you a scenario and be like, okay, here's something that happens in the real world. Tell me, in this scenario, what are the vertices? What are the edges? Is it directed or undirected? Is it acyclic or unacyclic? Again, maybe if there's a bunch of one-way streets, it's a directed graph. Maybe if it's Twitter, it's directed because if I follow you, that's a one-way direction, right? Maybe if it's Facebook, it's undirected because if we're friends, it doesn't matter who initiates the friendship, we're now both connected to each other. That's how those work, right? I didn't forget socials, great. Once you get everything into the graph format by answering these questions, then we can start to apply all of the clever algorithms that I'm going to start to teach you on Wednesday. So far, I haven't taught you how to navigate through this graph. I haven't taught you how to find whether something's connected to something else. But there's a bunch of great algorithms that tell you whether things are connected, how they're connected, to find you the fastest way to travel through something, to find you the fastest way to connect everything together. And so then you apply your algorithms to get your answer. Yeah, question? Is the A-star algorithm, is that what you asked about? Oh, okay. I am sorry, I don't know what the A-star algorithm is. Oh, okay. Gotcha. One of the ways that you can find your navigation through a graph, we're going to learn about something called Dijkstra's, and I will have a slide on Bellman-Ford. So those are the two particular algorithms that we're going to use in this class for shortest path. Yes. Dijkstra, great, cool, whatever you call it these days. Let's talk about an example. This was a midterm question I thought was so cute, but then crashed and burned horribly. So let's imagine that you are an American high school student and you have a very important note to pass in class. You do not share a class with the person you are trying to pass this note to. And let's be real, it's a love note. You're trying to pass a note to a crush. And obviously you can't just hand it to them because that's insane. So you are going to hand your note to someone in your first period class to hand to one of your other friends in their second period class and so on until your note eventually gets to your crush. Here is a possible example of some schedules here. Can anyone tell me, what do you think the vertices would be if I was trying to represent this journey in a graph? What are the vertices here? Yeah. The classes, sure. The people, for example, that's all those physical representations. What's the edge then? What connects people in this particular case? Yeah. Note passing. They share, I'm sitting next to you in class, I pass the note. Anywhere the note can travel along, that's going to be an edge in this case. So, here we go. We've got some graphs. Here's maybe you. Here's your crush. You have first period with Annika. Maybe Annika passes it in second period to Dan. Dan passes it in third period to Carla. And then, we have to figure out how to get it to your crush without the next morning. So instead, we would run a different algorithm, and we would eventually find maybe Dan eventually passes it directly to your crush. Just one way to think about how to represent things in graphs. I think I have another one in here, note passing. Here you go. You can look, I went deep into this. There's a lot of different things you can ask about it. You can optimize for time. You can optimize for risk. You can optimize for getting it to them faster or through the fewest number of hands, things like that. Here's another one, party planning. Imagine you're planning a party for your friend Steven. You want to figure out of your big group of friends who should come and who should not come. You want to invite as many people as possible, but you only want to invite either people Stephen knows or 1 degree of separation of friends. What are the vertices in this situation? People. See the patterns? What are the edges, maybe? Friendships. Boom, there we go. Maybe we've got a graph. And maybe we also don't want to invite 2 people that dislike each other, so maybe I colored those edges red. There are graph algorithms to tell us which group of people then should get invited to this party so that we only invite friends of friends and no red connections are traveled. We will talk about all of these in more detail. I'm just trying to spur your thoughts. Come back on Wednesday. We're going to talk about algorithms.